All right, let's see what we have about the announcement. Your lab number 3 has been released. Hopefully you got a time to look at that. It's quite important. And definitely your programming test number 2, that's going to happen in the final week, will be quite relevant to lab number 3. So I would suggest, while you're very busy preparing for your written test 2, this Thursday, also dedicate some time to lab number 3. It's going to be worth your time. And TA Maria, she will be in the lab session today. So if you got any question, reach out to her in the prison lab or my office hour. You're more than welcome to. Okay, lab number 3 is really important. And for your programming, for your written test number 2, how about we have some review session to answer your questions, like last time, okay? So why don't we say 7 p.m. tomorrow? It will be, of course, over Zoom. Try your best to make it there. If you cannot, I'll try my best to really make available the recording maybe later in the evening. I'll try my best. But it'll be nice if you can attend and just ask your questions. Okay, I'll send you guys the Zoom link a little bit later today. It's going to be a link different from the office hour link. Okay. All right, guys, any questions about this? Programming, it's been released since Friday. Okay, maybe check the announcement. 2 things you can check. Number 1 will be the e-post. You can check your marks. And number 2 will be the feedback file. You have to run a command from the remote lab. It's been released since Friday. So guys, if you really have concern about programming test 1, either reach out to me or if you want to submit a regrading request, it has to be done by this Friday, 5 p.m., I suppose. And the TA will look into them, okay, if you have any questions or concern. All right, let's now continue then. All right, so what did we achieve last time? Okay, so last time, I think, was mainly this diagram over here. We spent quite a bit of time explaining. I think that this is a very important diagram to really talk about refinements. The most important part to remember is, which we're going to dive a little bit deeper today. For any events that has an abstract counterpart, for example, ML_out has its abstract version ML_out as well. Also, ML_in also has its abstract version ML_in in the initial model. And we say that the concrete events should be simulated by the abstract event. You can see the exact wording in the slides. Okay? The way we relate these 2 events is by saying 2 things. Number 1 is about guard strengthening. We want to make sure if the concrete event is enabled, that means the abstract events should also be enabled. So that means whenever we have some occurrence of the concrete events, there should be a corresponding abstract event accordingly. Right? So we don't really create any new behavior. So if you go back to when we talk about a predicate being stronger or weaker, that's when we actually gain the intuition. So please make sure you go over that, just make sure you understand. And I'm not too sure if we can reach to that today. We're going to talk about another idea, which also has to use the notion about stronger versus weaker, which is something called relative deadlock freedom. If we cannot get it today, we'll get it maybe next Tuesday. We'll see. All right, so that's number 1, guard strengthening. Number 2, you have to make sure that invariant preservation should be done at the post states. And the way you do that is by, of course, formulating the corresponding proof obligation. Right? So these are the things we talked about last time. And the exercises for you will be these 2. Right? So I just gave you 2 examples here. Maintaining invariant number 4 using ML_out. And also maintaining invariant number 5 using ML_in. Right? That'll be exercise for you. You will be given something along this line on Thursday. Of course, it may not be this proof per se, but you have to know how to do proofs in general in sequence calculus. And also, as some of the example questions suggested to you, you also have to understand very well about the basic meaning about having a sequence versus having some inference rule. Okay, you want to check out the definition. Okay, and so for us to get started, I would like to start something very light. Okay, how do we make sure the events can establish the invariance? That's something very easy, but why don't we do that as a warm-up for today? Okay, so if you go to the slides, okay, so that's the diagram I just went over. Make sure you review it. And also we got these 2 sequence to prove, right? You can definitely look at the slides for solution. If you get any other alternative proof you would like me to check anytime, just drop by and reach out. We can take a look. Just remember the proof we showed to you on the slides is only one possible proof. In general, there could be multiple ways to do the proof. In the written test number 2, it's mainly just like a multiple choice. We're going to ask you to choose the correct choices. But for the exam, if we give you some new sequence to prove, it will be unbounded about how you're going to tackle the proof. And we're going to read it ourselves to see whether it will be valid or not. We'll talk more about it when we get closer to the exam. All right, so that's number 1. Pretty easy to check, to prove. That's number 2, which somehow will be split into 2 independent sequences by using the rule. And I'm pretty sure you know about this rule pretty well, right? Just make sure you know that for for Thursday. Okay, so let's do this one first. Pretty light. How do we prove that the refined system M1 can establish the invariance? Similar idea as before. So what we got to do is, so far we have done. So here I talk about some magic number, 12 sequence. Up to this point, you can also do the math. Why 12? Okay. So when we talk about invariant preservation, how many invariants do we have for the concrete model? You can see here, we got 1, 2, 3, 4, and 5. 5 invariants. For each one of them, we have to make sure it's maintained by the concrete events, ML out, ML in, right? So 2 times 5, that's the 10. And what about the other 2? It comes from something called guard strengthening for every old event that also exists in the initial model or in the abstract model. You have to make sure its guards strengthen the abstract guard, right? In the more abstract model. So that's why we got 12. And what we're going to do now is we're going to look at how we can establish an invariance. That was pretty straightforward. So this will be the init events. If you recall what A, B, and C are like, I don't have a diagram here, but if you remember, that's the island, that's the mainland, that's the breach. This part here is A, whatever that's in the island's B, and this part over here is C. In the beginning, we just have no cards in here, in either here or here. So A should be 0, B should be 0, C should be 0. Right? That one's straightforward. All right, and then we'll look at the proof obligation very soon. And here are simply some reminders to you. And this is also relevant to Thursday. Okay? You just have to remember for the initialization, it's a very special event where the pre-state simply does not exist. You're establishing the very first state for the system. So there's no state 0 before that. So there's only post-states available. There's no pre-states. So that's why the right-hand side over here, you can see, we can only put either constants or some, basically just constant, some concrete value. Can be empty set, can be 0. These are the typical initial values you will initialize the variable into. And of course, you cannot put any variables. So let's say on Thursday, if I put, let's say A becomes, let's say C plus 1, it's totally wrong, right? You just cannot refer to variable because they are totally uninitialized when you do the initialization. Okay, are we good about this? Okay. Let's now talk about how we formulate the proof obligation. So here I want you to pay attention to two formal components, and we'll see the correspondence very easily. One is about the K. So K here, which we spoke about before, but you can refer to the slide for brush up. K here is just about the actions we perform on the abstract model. Okay, for example, N becomes 0. Okay. On the other hand, we got also L. You can see K here and L here. L will be whatever initialization actions we do to the concrete variables in the M1. In this case, A becomes 0, B becomes 0, and C becomes 0. Okay? So the only 2 components you have to pay attention to will be K and L. Right? And let's now take a look. So that's the conceptual sketch here. Now, I have one quick question for you guys. Okay? It's a very quick check. If you look at the proof obligation here, okay, that's for invariant establishment, not preservation. Okay? Here we're saying that invariance that's indexed by I. Here I could be 1, 2, 3, 4, or 5, right? So it could be 5 possibilities. And is there any reason why not we actually put the invariance over here? I'm saying that I'm assuming that before the initialization, the invariant should really hold. And the invariant might involve both the abstract and concrete variables. Is there any reason why this antecedent is not there, or hypothesis is not there? Well, I just made a typo. It should be there. Adnan. In the initialization, that's exactly right. Right? So guys, if I really want to confuse you in the test or the exam, I might say, is the following the correct initialization proof obligation? Apparently, it is not, because there's no pre-states. All right, just remember. Okay, I want to emphasize that again. So important. Here will be not applicable, okay, because there is no pre-states when initializing the system. Okay, just remember. Okay, and then let me remind you again. So here, the K here is the abstract initialization steps, and the L here is the concrete initialization steps. Okay, and pretty easy proof obligation. And why don't we try to answer the basic question first? How many do we need? How many, well, this is a single proof obligation rule. How many sequence should we generate from here? In case you need hints, but why don't I take your answer first? Go ahead. 5? Why? That's exactly right. We have only one init events, and then we got 5 invariants to establish, right? Exactly 5. Very good. Okay, so this answer will just be 5. You can think about init and also 5 invariants. That's exactly right. All right, so now let's generate some of them. I think the example I got. Okay, why don't we do 1, and I'll assign one of them to you as an example. So let me write down the rule name. Okay, so we can say init, the event name, and also let's say invariant number 4. And then we just put INV. So for invariant establishment and preservation, we both put INV. How can we tell the difference? Well, when you look at the name of the events, if it is init, so that must be invariant establishment. If that's not init, for example, ML out, it must be about preservation. You can tell the difference. Okay. All right, so for this one here, let's not waste your time. Why don't I give you the answer directly, but I'm going to give you some exercise to try. Okay, for this one, we're going to put axiom. Okay, these two are the axiom, which will be D is a natural number and D larger than 0. And then turnstile, and over here, there's going to be something we got to put, right? And for that one there, we want to focus on invariant number 4 over here, which is over here. There's only post states available for invariant establishment. So for this one here, I'm going to calculate over here. It's going to be A prime plus B prime plus C prime equals M prime. Are we good so far? All right, that's a kind of intermediate calculation, which I would really recommend. If you really haven't got very used to about substituting values on the fly, you may just want to do some intermediate expression to help you, so you wouldn't make any mistake. Okay? So let's try to take a look. You can see these 3 are the abstract variables. So we have to look at the K, the abstract initialization, which I didn't include over here, but if you recall in the init events in the M0, it will simply be, remember, oh, I beg your pardon. Let me say it again. So A, B, and C here are the concrete variables. So what we should look at would be the L. Okay, again, my apology, I just made a terrible mistake. So these 3 are the concrete variables, so we should look at the L to see how we initialize each one of them. So here we got A, B, and C. The before-after predicates will be A prime equals 0, and B prime equals 0, and C prime equals 0. Okay, so what we got is 0 plus 0 plus 0, right? That should be equal to, and here is what I really meant to say. This one here is an abstract variable. In that case, we have to look at k. And if you recall the init events back in M0, it simply say m becomes 0, right? In that way, we're going to put 0 here. Well, looks pretty straightforward, right? So I would say here you can simplify it, or you don't need to simplify it. I would say it's kind of up to you. But let me just not simplify it. So the final answer should be 0 plus 0 plus 0 equals 0. I'm pretty sure you will know how to prove this by applying the relevant inference rule. I would suggest give a try on discharging this yourself, and you will see answers on the slide as well. Okay? And one more exercise for you. I would like you to also formulate and prove this one here. So this will be also initialization, and then we got invariance 5. Oh, in the previous one, it should be INV 1. Okay, forgot that. And then that one there is also for invariant preservation. So you want to formulate, and you want to prove. So that will be some simple exercise for you. All right. Guys, are we okay so far? Right? Up to now, it's pretty light. It's just about establishing invariance. You just have to make sure you remember there's no pre-states for the initialization events. All right. If no question here, and I'll leave this part here empty for you. All right. So you can take a look and do the exercise. They are very easy. I even tell you, these are the 2 relevant inference rules you can use. Okay. All right. Any question? Very good? Yes? Sorry, say it again. Which one? Sorry. E2? Oh, 0 equals 0? You mean arithmetic, right? Oh, I see. So typically, when I put the inference rule over here, I'm just saying the ones on the PDF, the sheets. But if you want to use arithmetic like ARI, you can also use it if you need to. That one, ARI, that's a good question here. I would say ARI, you can definitely feel free to use it. But I think in the written test number 2, it will be very clear in the context whether you can use ARI or not. So it's just multiple choice, so it should be okay. But I think for the exam, I'll try to give you guys a little bit more tips about whenever you use ARI to be safe, what in addition you should really write for the TA and for myself. Okay? So it's usually for simplification. Yes, you might need it. In that case, feel free to use it. Okay. All right, very good. And good, we're only about less than 20 minutes. I think today we're going to now start talking about the trickiest part for the refinements. It has to do with events that do not exist in the initial model. And then we have to talk about some scenario or phenomenon called divergence. And also when you talk about how we can use something called variance to really mention about the possibility of having divergence. Okay, let me write down the roadmap, and then we should really talk about each one of them. Hopefully we can finish this trickiest part today. Then we have achieved a lot. So we're going to talk about, number 1, let me start with this. When we talk about how we categorize the events. So if you recall, we have our initial model, M0. And the current model that we are talking about, the first refinements. Of course, we have some formal refinements relationship over here. And whatever events that's in the M0, we just call it abstract events. Okay. Abstract events. Okay, over here. And of course, we got ML out, and we got ML in. All the events that exist in M1, we call them concrete events, all of them. However, we can subdivide them into 2 categories, old versus new. Okay? Concrete events that are actually old, meaning mean that they actually already exist in the initial model. In this case, obviously, it's going to be the ML out and also ML in. And these are the ones we have already dealt with so far. All right, just to remind you, we actually got guard, strengthening, and we got invariance, preservation, and also we got invariance establishment. Right? These were the three things that we did. Right? Just to remind you. What we're going to talk about now are the events that are concrete, but they are also new, meaning that they didn't really exist in the initial model. Okay? Let me write it down. The new events. In our case, IL in, IL out. Two events. Okay? So these are going to be the two events we're going to focus on for today. And there's several issues over here. Let me give you a roadmap, and then we have to dive into them deeply. Okay? Number one. Of course, we have to talk about their guards and also their actions. We'll do that first. Number two, we said before, the concrete version of ML out, for example, is simulated by the abstract version of ML out, right? Let me put it down. The ML out over here versus the ML out over here is, so thinking this way, is simulated by, don't get the direction wrong. You would say the old events is simulated by the abstract events. Okay? And now here's one issue for us. IL in, IL out. Which events in the abstract world simulated? There's no, seems like. All right? So there's something we have to deal with. Okay? IL in is simulated by which abstract events? Strictly speaking, there's no corresponding abstract events. But what's going to happen is we're going to create some artificial events going to going to correspond to ML out, sorry, IL in and IL out. Okay. Right, there's a big question over here that we're going to address. Okay? And number three, once we get number two addressed, we're going to talk about something called divergence. And I'll get there a little bit later. Number four, we have to talk about something called variance of the model, right? So these are the four issues. So when you review this part of the lecture, maybe for your exam, you want to make sure, always remember, these are the four aspects you have to pay attention to. Let's go one by one. The first one here is the easiest one. Why don't we go with that first? Okay. Down there, we should really fill out the guards and also action for IL in and IL out. Okay. So let's look at this slide very quickly. Okay. Yeah, that's one just from before, and that's the slides for the, that's the part for the answer, for the exercises. Okay, new events. And this part here, just the same as before. We are treating our model as a state machine. And we want to make sure whenever the actions for the event should really occur, it must be enabled in the first place, right? Always the principle. And we're going to talk about IL in and IL out. Okay? So this second bullet point tells you we already consider the refined events, the old events, ML, ML in. Let's now consider IL in and IL out. Okay? Let's remind ourselves what these two events are about. We briefly mentioned them when we first talked about the refinements. But let's take a look at the diagram. Okay, so that's the abstraction for the first refinements. So that's a bridge. So you can think about ML out means the car is going to leave the mainland into the bridge. MLN means some car from the bridge is going to go back to the mainland. Now we got two events over here that we got to address. Let's say there is already some car moving this way. Now the car is reaching the end of the bridge over here. They want to move into the island. So that one is ILN. Similarly, let's say there's at least one car over here, let's say in the island. That car wants to go back to the mainland. In order for the car to do it, they have to, first of all, go onto the bridge, if they are allowed. And then, once they go onto the bridge, it's called IL out. So now we got 4 events that's complete. All right, just make sure you understand the definition or conceptual meaning for IL in and IL out. Okay, it's so important. Okay. All right. Let's now, okay, and the axiom, the variables and invariants, they are just the same as before. And I put these as question mark so we can fill them out very quickly. Let's see the principle. For ILN, the hints would be, we want to say ILN, whenever we got ILN, that means a car entering into the island from the bridge, right? Now, when should that event be enabled? Right? I agree. Yes, and that's most it, right? Okay. I think that's definitely one of them, but let's write it down first. What Nathan said was actually 100% right. So the bridge current traffic flow to the island. Okay. So this is to say, if you want to do ILN, so that means there should be at least one car heading this way, right? So that means A should be larger than 0. Okay, so that one is obvious. Okay, so this one here is going to be A larger than 0. Question? Oh, you mean there's no car going there? You're saying, for example, should we also say, let's say C is equal to 0? Yeah. Okay, good question here. The answer is, it's not incorrect to say that, but it's unnecessary. Because if you look at the invariant over here, it tells you either A is 0 or C is equal to 0. Now that we know A is not equal to 0, it's got to be that C is equal to 0. Oh, so it's already logically implied. Okay. If you put it on the exam, would that be wrong? It wouldn't be really wrong. It depends on what the question was. If the question simply say, put on the appropriate guards for these events. In that case, you put something that's logically already logically implied, you definitely will still get most of the marks. That's not a problem. Okay. But on the other hand, if we phrase the question more like, only put that's what's logically necessary. In that case, you might lose a little bit more marks, right? Okay, so I like that question here. So let's say this one here, not necessary. Because of invariance 1.5. And I'll pose one more question that's along the same line in just one moment, so you guys can think about. But let's before that, what should be the action? Okay, let's say here, if I got one car over here, okay, and the car is now moving off the bridge and go into the island. In that way, what variable should I change? A and B? Yeah, exactly, right? So that means A here should be decremented and B here should be incremented, right? Okay, if you guys are comfortable, I'm going to write it down. So this one here is going to be A becomes A minus 1 and B becomes B plus 1. Okay, just make sure you're okay with this. I'm going to present another guard. And you guys tell me whether or not it would be, number one, whether or not it's necessary. Okay? If not, why not? So the question is, if I put another guard over here, which is to say A plus B over here less than D. If you look at that, so here you can see, remember one of the invariants back in the initial model. We want to say the sum of all the flow, the number of cars in both the island and also the bridge should be less than or equal to certain limits over here. But here I'm just saying that since I might have to add something, so I want to make sure A plus B over here should be strictly less than D. Would that be necessary? I heard no. Okay. And Rafa. Yes, that's spot on. Very good. Right, guys, I think this question here is very important for you to think about, right? This also tells you whenever you're designing the guard, you don't really just want to put, it's not like the more the better. Not really, right? And also, even though something may not be hurting, but if that's not necessary, you shouldn't really put it, okay? So there are two things I want to say about this guy here, right? The answer is not necessary for two reasons. You guys can think about it. Okay, number one, ML out already checks it. Okay, if I can just go back, so let's just convince ourselves. That's a long time ago, but let's now do that quickly. Okay, I think it's when we first talk about the initial model. Over here. Yeah, there we go. Sorry. If you look at ML out over here, you can say A plus B less than D. Right? If you think about it, what's happening here was when the car is first moving from the mainland into the bridge, ML out would have already checked that you wouldn't exceed the total capacity that's allowed. So once the car is allowed into the bridge, you don't have to check it again. Right? In some ways, too late. The car is already on the bridge. So you would have checked that already. So there's no point to check once more when the car is about to move from here to here. All right, that's point number one you want to remember. Okay? Let me go back and tell you another aspect over here. So, sorry, over here. Okay. Another aspect you can consider would be okay. So here we are talking about really this particular quantity, right? It's going to be A plus B, which would be the total number of cars in the island and on the bridge. So if you think about it, it's going to be A prime plus B prime, right? After the events is executed, so A is going to become A minus 1. B is going to become B plus 1. This will just be A plus B. So this tells you, as far as the total number of cars is concerned, this event is not going to modify anything. So there's no concern about checking this. And number two is going to lead to another very important conclusion. Okay? I'll sketch the idea a little bit, but that's something I'll talk a little bit more precisely. Guys, again, number two tells you, since A is going to become A minus 1, B is going to become B plus 1. Okay? Now, if you think about A plus B will just remain the same. That means the corresponding N, which is the number of cars here, right? A plus B plus C, also remain the same. That tells you for this particular new events, as far as the abstract model is concerned, it really makes no change on N. Okay, that's something I want you to think a little bit more. Okay, I'm going to visualize it in a bit. That also gives some justification about how we can find the corresponding events for these new events to the abstract world. We'll see that. Okay. All right, so that's about IL in, and for IL out. Question. Yeah, it's unnecessary. Yeah, I see. Unnecessary in the sense that we don't really need to check about being about possibly exceeding the maximum capacity anymore. So we don't need to put it. We don't need to concern about it because at this point we have already checked in the ML out. So we don't. It's unnecessary to check it again. If you put it there, yes. If you put it there, it might make some. I'm not too sure if that would make a difference, but I would say we just don't need to concern about that. Mm-hmm. 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 Yeah, sure. Yeah, so I would say let's not really get down to that particular part. I think it's important to know at this point over here, when we talk about ILN, we don't really need to concern about the maximum capacity being violated anymore because that one would have been checked already. That's the point. Yeah. Mm-hmm. Okay, very good. Okay, let's now talk about IL out very quickly. Okay, for IL out, that one there is going to be, yeah. So IL out means the car is going to exit from the island onto the bridge. Okay, that one should be quite symmetric. It should be enabled when there's at least one car in the island. Right? This one should be rather straightforward, more straightforward. Right? So here, if we want the car to really exit from the island, we want to make sure B is at least positive. Right? Should be at least one car. So here we're going to put B larger than 0, and is that enough? Yeah, exactly, because if I want to go this way over here, I want to make sure the other traffic should be 0. Exactly, right? A equals 0. That's why we've got these two guards. Okay. Want to make sure at least one car is there in the island for us to exit. Number 2 would be the other way, traffic has no possibility of collision. And over here will be easy. It simply just decrements B. B should be B minus 1. At the same time, we are having one more car onto the bridge. So C will be C plus 1. All right. Yeah, think a little bit more about how to interpret these events. I mean the MLL, MLN, ILL, ILM. Yes?
So for the A equals 0, the reason why we add that is because if B greater than 0 is not the same as invariant 5.
No. That one, yeah, that's true. That's true. Because B larger than 0 has not, wouldn't imply anything about A being equal to 0. Right? Because you can see this invariant here involves both A and C. Yeah. Yeah. The reason, okay, I see your point. Here, we don't really need this. Sorry. We don't really need this. It's because A here is already not equal to 0. So C got to be 0. On the other hand, if we know that B is larger than 0, but B doesn't occur over here, so it wouldn't help anything. So you still have to say A is equal to 0. Right. Good? Good. All right. And let me talk about one more thing, and then we'll take a short break, and then we get to about finding the corresponding event for ILN, IL out. Right? Let's just do one more very quick summary. Okay. So this will be the final version for ILN, IL out. You know, the concrete guards, concrete action, and over here. Right. The only thing I just want to mention is about before-after predicates, which will be very necessary when you want to talk about invariant preservation to formulate a proof sequence. Before-after predicate will be, apparently we got A and B, and C is implicit. That means it should remain the same. So A prime equals A minus 1, B prime equals B plus 1, C prime, C. And similarly for IL out. Well, that's the only thing I want to highlight. Okay, just don't forget how to derive the before-after predicates. Any questions? All right, why don't we take a short break, because the next part is going to be the trickiest part that we're going to need to understand. Why don't you guys take your device, and then let's take a quick attendance, and then we'll let you take a short break. Okay, start a class. There we go. And the poll. And then here. All right, you can check in, please. Yeah, we are taking attendance now. If you got any issue, I got a sign-up sheet for you. You can come to the front. Everybody's good? Okay, I'll wait for just one more moment before I shut it down. All right, thank you so much. All right, let's take a 2 minutes break, and then we'll come back. Okay. Hi. Yes.
I can come a bit early for the office hours.
Office hour?
Yeah.
How about 3:15?
Yeah, that works.
Yeah, sounds good.
Thank you so much.
See you then.
Thanks.
Hello. Hi.
Question about
Yes.
when you declare the actions.
Yes,
You're
yes.
always presenting it the way we do in Rodin, but also like the way with the before-after predicate. So in the exam, like which one should we be presenting our answers?
Oh, I see, for the action, right?
Yeah.
So if I say, okay, so if I say I want you to fill out the action for the events, in that way you got to do the call and equal. That's more like a Rodin way.
Okay.
But if I say, if you want to formulate a sequence for, let's say, invariant preservation, in that way you will need the before-after predicate
before-after
to do the
predicate,
substitution. Yeah.
But if we're just presenting, like we're just constructing the event as is, right? So it would just be the way you write it in Rodin.
Yes, that's
Okay.
correct. That's correct.
But sequence, it's the before-after predicate.
That's correct.
Okay.
Yeah, good. Hello. Oh, you didn't get there in time?
Yeah.
All right. There we go.
Okay, thanks.
Yeah, maybe on the second page, I think.
Yeah.
All right, guys, 1 more minute, and then we'll get started again.
Thank you so much.
Thank you.
When is today's office hour?
Today?
Yes.
3:30. Yeah.
Do we have office hour tomorrow?
Yes. But tomorrow, I might need to start the office hour a little bit earlier. So I can tell you today could be a little bit busy because my students from 4350, they're having a test tonight. There might be more people dropping by, but you can try if you want to. Or tomorrow. Tomorrow will be very quiet, I presume.
So today will remain the same or
3:30,
3:30? So tomorrow will be earlier?
maybe 2:30.
2:30. Okay. Thank you.
Yeah.
And at 3:30?
Huh?
So when it ends for tomorrow, it will
1 hour, so 2:30 to 3:30.
because I have a lecture start at 2:30.
2:30. Oh, really? You know, if that's the case, maybe just come today. You know, it should be fine.
Yeah, but I just thinking about like I have some questions I want to ask today, and I want to do some exercise. And
Oh, I see.
so
And then
we
come
can
back.
do
Okay.
tomorrow.
If that's the case, send me an email and then tell me your schedule for tomorrow afternoon. We might be able to just meet either earlier or later. Yeah. Okay.
Thank you.
Okay. All right, guys. We'll start in just one moment. Okay, let's get started again. Okay, we got about maybe 35 minutes or so. Okay, let's see how much we can do. Okay. All right, so let's do a very quick recap about what the events we have seen so far. Because I think later on when we talk about different concepts, we may have to use the idea about trace of the system. So you really have to know what does it really mean what will be the logical flow for the event to really occur? Okay, let's now take a look. Okay, so this will be so one possible system trace. So let's say if we got one car traveling, okay, in that case, the car is going to be maybe from here, and then it's going to move to the bridge, and then it's going to the island at some point, travel a little bit, and then it's going to move back to the bridge, and then go back to the island, the mainland, right? Roughly speaking, right? And when the car first goes from the mainland to the bridge, it's going to be ML out. And don't forget, we also got init. So we got ML out. So now the car is on the bridge. And the car is now going to enter into the island. IL in. And then the car, let's say they want to leave. So it's going to be IL out, exiting the island. And then finally, they're going to go back to the mainland. Pretty straightforward. That's the logical flow for the simplest scenario. Okay? What you want to think about is this. What about I have two cars traveling? What can be the possible interleaving of the events? That's something I'd like you to try. Two cars traveling. And I can tell you that there will be more than one possible traces, right? For example, let's say the first car goes, and then before the first car ever reached to here, we got another ML out, right? And then maybe they will enter into the island one by one after another, and then the first car wants to go back, and the second car is staying in the island for longer, right? So you want to think about the different scenarios and what should be the corresponding traces. So that will be the exercise I would like you to do, because we need that kind of a tracing ability to understand certain concept. Okay? Yeah, that's what I want to start with. All right, so let's now go back to the IL in and IL out. And we want to think about what events in the abstract model can these two events correspond to. Okay? Okay, that's before after predicates. Okay, this is important. Number one, IL in, IL out. Strictly speaking, there is no corresponding events in the abstract world that we define as a modeler. So now we have to make up one event that's actually going to correspond to the effects of IL in and IL out. Okay? And the idea we're going to use, before I draw some diagram, is, let me remind you before the break, when I was talking about this guy over here, right, let me recap very quickly. You can revisit this point a little bit later. If you look at IL in, its effects is going to be on A and B. One will be subtracting 1, the other one will be plus 1. And what we really care is about the n in the abstract world, which is going to be A plus B plus C. Okay? Now, if I do A prime plus B prime plus C prime, it's going to be A minus 1, B plus 1 will cancel out. We still got A plus B, and C doesn't change. That means n here also doesn't change correspondingly. So what we really need is an artificial event that would do n becomes n itself, basically. That would be the events we want to talk about. Okay? It's a special event. Similarly, if you look at the effects for IL out over here, that one there, you got B and C. One is subtract 1, the other one is plus 1. And here, if you try, for example, A prime plus B prime plus C prime, that's going to be, again, A prime will just be A, right? Because you can see A is implicit over here. Plus B minus 1 plus C plus 1. You will still get A plus B plus C, right? That one there is simply equal to n. So it will be as if there was no change on the abstract variable. So the principle will be, for every new event, if your design was correct, they should really correspond to some special occurrence in the abstract model where the abstract variable does not change its value. Okay, so that's kind of the intuition you want to get. Right, it's a little bit hand waving, but I would suggest we do a little bit of more concrete drawing and see what's going to happen here. Okay, let's take a look. And the events I just spoke about is called skip. Okay, so ILL, ILN are the concept for the refined model. They correspond to skipping in the abstract model. And the skipping there, you can see begin and end. There's no action. You'll be as if n prime is equal to n. Okay, let's see exactly how this can be visualized. So guys, as I said, don't feel too bad if you're not really grasping that for the first time. It's kind of tricky, right? So what you have to really bear in mind is the diagram over here. Let's take a look at that together. All right. And if you guys remember before, we talked about ML out, the old events has its abstract counterpart. And we simply show that in the pre-state and post-state for the ML out. We can simply relate the variables using a plus b plus c equals n, right? A plus b plus c equals n. That's something we said before. Okay? What we want to do now is, what if I do another transition here, IL out? Meaning that events going into the bridge, they are now heading to the island. And what should this really correspond to in the abstract world? We want to show you that it will simply correspond to something called skip, which does nothing. Right? We want to convince you that's really happening. Okay? Let's do that. And I'll summarize something important over here on this diagram. Okay? That's what we'll do. All right, so to really read this part here, let me just brief you very quickly. So ML out, right? That one there, the concrete version is simulated by the abstract version. You can see initially we got 0, 0, 0 for ABC. ML out is going to increment A into 1. Okay? So what I want to do now is, maybe I will just change the color of this so that you can focus more on the new bits. Okay? Let's say we want to do IL out. So think about we have already done ML out. So now we want to do IL in. Okay. So what I will do is I'm going to do IL in. This one here. Okay? And then how should the state change? Let me put it here and put it here. Okay, that one there, let me just do from scratch. According to the events for IL in, oh, bless you, IL in over here, it will be A minus 1 and B plus 1, right? So what I should do is I'm going to decrements 1 into 0. Increments B from 0 up to 1. And C here remain 0. Are we good? Okay, that's just about making a concrete transition. Okay? And then we want to decide what the corresponding abstract transition should be. Okay? Let me put just question mark just for now. Okay? And then we're going to put the states over here. Oh, sorry, not this one. Let's put the states over there. Okay. Okay, let me wipe it out just for now. Now, how can I work out exactly what's going to happen in the abstract world? Let's get help from the invariants. Okay. And I'm going to relate these two states by that so-called linking invariance. And that one there is invariant 1,4. Okay, I'll write it down here just to remind you. Invariant 1,4 is A plus B plus C equals N. So whatever corresponding events we find over here must be such that the invariance is still maintained. Okay? So what we want to do now here is invariant 1,4 will be A prime plus B prime plus C prime. Okay? For that one, we know that it's going to be A minus 1, right? You can see A minus 1 from 1 to 0 plus B plus 1 and plus C, which will be A plus B plus C. Okay? And that one there is simply equal to just the n, exactly over here. Okay. And then this will be just the post-state value at the same time, n prime. So what's really important for you to remember is, based on this, we will know that this part here will end up being just n. And n at the same time is also n prime. So what we really need is to look at this particular relation here and then make it the before-after predicate for the corresponding abstract events. That will be exactly like a skip. Okay? Because the skip over here, it would be as if n prime is equal to n. In that way, n prime will just remain to be just 1. Okay. Okay, let me recap. And then if you got any question, confusion, please let me know. What we're doing here is, before we talk about the old events corresponding to some events already exist in the abstract model, to really see how they are corresponding to each other, we can use some invariants involving the abstract and concrete variables. We're doing something very similar right now. Here, we're still making some transition in the concrete model. And this event here is I of n. And we already see the transition effects. And based on invariant number 4, we can see that because I of n has been done in a particular way, which will subtract n plus, that one will just give us just the same abstract variable as before, just n. So this tells us to find the corresponding abstract events, it should be such that it has no effects on the abstract variable. And the best way to do it would be just having by having a skip events over here. Okay, so that's why we got to skip. And the conclusion is, for any new events in your refinements, the corresponding abstract events should be just skip. Okay. This one is tricky. Think about it, and possibly later on when you review this for the exam, ask me again. Maybe we can have some review session. We can talk about this concept again. But you do need to think about what's the sequence of reasoning over here. Okay? So here we start with the concrete transition here, and then we work out the logic to see there should be no effects on the corresponding abstract variable. So that's why skip would be the most appropriate events to have. Okay? Guys, any quick question if you have? Yes? Well, the problem is, if you only got I of n, but you want to see what the corresponding event is, if you don't have things like a skip, then you wouldn't be able to work out how they're related to each other. It will be the same, because, yeah, so the idea will be the same. So if you look at I of out, that one there, here, so the before-after predicate here, b prime equals b minus 1, c prime equals c plus 1, and also a prime equals a. What the same. So now if you look at this part over here, a prime plus b prime plus c prime, it would be a plus b minus 1 plus c plus 1. And minus 1 plus 1, again, cancel out. So you will get a plus b plus c, which is also equal to n. So you're getting the same conclusion. So that's why I said, given that your new events have been designed properly, they should really correspond to the skip events in the abstract model, which has no effects on the abstract states. Mm. Okay, good. Okay, let's now move on a little bit. Oh, just before that, let me just annotate a little bit more. So what we have is this. So here we have, this will be the new events. The new events. For example, IL in. One example. And that one there should really correspond to the skip events. And the way we relate them, for example, in the pre-states and also in the post-states, is by that invariance. pre-state, and also the post states. For both of them, we just use invariance 1.5. Invariance 1.5 to relate them. Okay. Again, this is really tricky, I know. Kind of weird, but that's the way we can make things work mathematically. Okay. And let's now take a look at something a little bit simpler, and then we talk about something called divergence. We'll get there. Okay. How do we make sure the events ILN over here actually will preserve the invariance? That's actually important, right? So that will be the next one. Okay. If I go back to the slides, right, that's the skip that we talked about. And what about invariant preservation? And this one here, don't think this is like a special case. Both the new events and the old events, they should both preserve the invariance. So the way we're going to formulate them will be just the same. Okay, so I'm going to do one very quickly, and the rest will be exercise for you. Okay, it's more like a review. Okay, about invariant preservation. Okay, so we got IL in, IL out. And how do we formulate them? That's the proof obligation rule. Right, we got axiom, we got invariant at the pre-states. We got abstract invariant in the pre-states. We got concrete invariant at the pre-states. We got a concrete guard. In this case, maybe ILN or IL. Yeah, let's say ILM. And also, this will be the actual invariance in the post-states we want to preserve. Right? This part here is just the same as before. Nothing new for this part. Let's just do one for example. So this part over here will be the axiom. So we're going to put a natural number, and also d larger than 0. Okay? And then this will be the abstract invariance, which is over here. So that will be n is a natural number, and also n less than or equal to d. Okay? And then we have the concrete invariance, which is over here. Okay? A natural number, B natural number, C natural number. Okay, I might need a little bit more space. Let me just put this down a little bit. Okay, okay, that should be good. And then we got this one and this one. A plus B plus C equals N, and also A equals 0, or C equals 0. So far, so good. So these will be the common hypotheses that any invariant preservation should really share. Right? So now, when we get down to the specific events, let's say ILN. In that case, we need its guard. ILN, the guard will be A larger than 0. So I'm going to put it here, right? Just separate. I just don't have space. You know what? I should be able to create space. Let's say A larger than 0. And then turnstile. Right? So what should I put over here? Depending on, but if you look at that one there should be indexed, right? Now I'm talking about invariant 1.4, which is over here. Now, what should this be? Well, we've done this many times, right? Yes.
C prime equals N prime.
And then do the substitution, right? Very good. Absolutely. And so for the question mark over here, you're going to say A prime plus B prime plus C prime equals N prime. And of course, that wouldn't be the final answer. You have to make sure you look at it before after predicate. A prime should be A minus 1 plus B prime should be B plus 1. C prime, which is implicit, the same. Equals, and now, guys, big question. What should N prime be? Before, okay, I tell you before, when we talk about ML out, let me go back there, to be very precise. Otherwise, this part you can just get confused. Let me go back to the invariant preservation part for ML out, for example. Okay? So when we talk about ML out, and then you can see that this part over here for ML out, the way we calculated it is by using the before-after predicate, right? So here, this will be A, B, and C. And what about N? It will be the corresponding events for ML out, which already exist. Okay? But now, let's go back to our current situation. For our current ILN, there is no ILN in the abstract model. So what should we replace M prime by? Ryan? Exactly. All right? So up to this point, we already assume for every new event, when you try to formulate a sequence for invariant preservation or establishment, the before-after predicate for abstract variable should be just corresponding to the skip events. Okay, that's really important. Okay? So this part over here should be the skip events. Okay, so just replace it by N. So the final answer should be A minus 1 plus B plus 1 plus C equals N. So what you guys really want to make sure you follow is about M prime here should be really corresponding to the skip events. And if you look at the skip events, should just have M prime equals N. Okay? That will be one. And of course, you can prove it. All right? Exercise. Okay? And for this one here, how do you formulate it? That will be also exercise. And solutions are also on the slides. Formulates and proof. All right, that's what you have to do. All right, if you go back to the slides, right, so for invariant preservation, and here that's also very important. When we talk about invariant preservation just for the new events, how many sequences do we need? The number of new events, in this case, 2, ILN, ILL, multiplied by how many concrete invariant do we have? 5, right, 2 times 5. Okay, that one should be also straightforward. And then, so these are just 2 examples I put on the iPad page. And then you guys can actually try to prove this one here and this one here. Okay, these 2. They're not too bad. All right, I'll let you guys do it, but you can take a look. The second one turns out to be slightly more complicated, slightly, but it's not too bad. Okay. Okay, I think we got about 10 minutes. Okay, how about I'll just take about 5. I just want to talk briefly about divergence and then give you some quick idea, and then we'll continue from next Tuesday. Okay, so I think this part here is really important, so I definitely don't want to rush. Otherwise, you'll just get even more confused when we get to the second refinements. Okay, good. Now, let's look at this example model. Okay, this one here is very bad. I can tell you, first of all, very bad. Okay, but why it is bad is important to realize. Okay, let me tell you, this one here looks a little bit similar to the M1 that we have talked about so far. I can tell you what the differences are. Number one, we got only 3 invariants rather than 5. So the only invariants we have are A, B, and C just being integer. That's it. That sounds like a good news because that means we got less proof obligation to prove. Right? It's almost like when you have a software that's to be tested, you only got 10 test cases to pass rather than 100. Should you feel happy about having so few test cases to pass? Not really. Right? So I would say whenever you got very simple and a small number of invariant for your model, that's not necessarily good. Okay? So invariants are only a few. And you can see ILN, IL out. We still got ML out, ML in. They're the same. If you look at IL in, IL out, I still got the same actions as before. That part doesn't really change. But now I took out their guards. Okay? So now, what we want to somehow anticipate is to see how bad this model can be. I'm pretty sure there might be a way to really result in maybe a clash with the car, but that's not what I'm looking for. Okay? I want to show you directly about the following. Okay? So now what you want to look at, number one, let me make some very quick points. If you look at this part over here, when you have fewer invariants than necessary, it's called your system is said to be under-specified. The system is under-specified. Because number one, safety properties are missing. And if you recall, in our correct model, we say that A equals 0 or C equals 0. That's a typical safety property, but it's not here, so that's not good. Okay? It's missing. Okay? And also number two, linking invariants. And whenever I say linking invariants, it's an invariant that's going to link the abstract variables to the concrete variable to see how they're related. But now we don't have that. That means anything is possible, which is not good. Right? Everything should be really constrained in a good way. Are also missing. For example, when we say A plus B plus C equals N, that one's not there. Right? So these two will take them out. Right? So this is going to give you some example about a bad model when you only have typing invariants, which means only specify the types of the variable. That's not good enough, for sure not. And one thing I want to give you as exercise and aside. All the proof obligations related to invariance preservation can be discharged. How? So here I'm saying that even though I claim that to be a very bad model, however, all the proof obligation we talked about before, if you try to generate them with respect to these three invariants, you can easily discharge them. So we can say that the model is provably correct only with respect to these three invariants. But the problem is the invariants themselves are not complete. So your claim correctness is also not complete. Okay? This will be what I want you to try. Okay? And then I'm going to talk about divergence very quickly, and then we're done. But since the invariants that we have over here are incomplete and lacking, the notion of correctness is pretty weak. Right? Because you're proving things with respect to something that's incomplete. Right? It's like in your JUnit test case, if you get a green bar, does it always mean something good? Not necessarily, depending on how complete and how good quality your test cases are. Similar idea here. All right, so let me show you one system trace, and then that one will really give you some example about something called divergence, and then we're done. Right? Just a few minutes. Okay. What I want you to try is this. Let's say we have some concrete transition. Okay, and then let's say we got init, okay, and then I have ML out. So I do have the first card moving from the mainland into the bridge, okay? According to what I have over here, okay, I can do IL in, IL out, IL in, IL out, and etc. I can do as many IL in, IL out interleaving as I want, indefinitely. Why? Because here, number one, these two wouldn't change the total sum of A, B, and C. And over here, they're unguarded. I can do as many interleaving as I want. Okay? And now, what would they correspond to? This will be my final remark, and then we'll pick up from here, maybe next week, just to dive a little bit deeper. What about the abstract transition? If you look at that, it's going to be init. Right, the same. ML out also correspond to the ML out. And remember, both new events will correspond to skip. Right? So what we're going to have will be skip, 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 and skip, and etc. Okay? Now, if you look at the concrete transition, there doesn't seem to be anything that's wrong because you still have transition there. There's no deadlock. You always have one event enabled for you to take place. However, if you look at the abstract transition, this looks something not good. Can you guys relate anything that you learned maybe back in 2031, or maybe operating system course? LifeLock is the term, but have you guys ever written something like this before? You say something like a while true. And then here I would say I'll just keep waiting until maybe the mutual exclusion lock is given to me. But the problem is I'll never actually get the access to the lock. In that case, I'll just keep busy waiting forever. In some way, the system is still making progress by waiting, but it's really wasting all the resources by waiting for no reason because you're waiting indefinitely. So that's exactly what this scenario is about. That's something I'll try to continue from next Tuesday. Okay? So guys, I would say after Thursday, the test, you will try to study up to here to make sure you're getting these two traces about the skip events. And then we got to talk about how we can prevent or check about this scenario. Okay, I'll see you there maybe over Zoom tomorrow.